Hello everyone, this is Bingbing Xie, a second year PhD student from UMass Amherst. Today I'm going to present our work, Tagtag Material Sensing with Commodity RFID. So this work is a collaboration between UMass Amherst and Northwest University. Now let's get started. RF sensing has been a hot research topic in the last few years, and many exciting applications have been enabled. For example, localization, HCI, and human tracking. However, we observe that little attention has been paid to material sensing. On the other hand, material sensing is actually important and plays a creative role in many real-life applications. For example, robot control. With material sensing, a robot could intelligently reduce its strength if it knows the target is an egg instead of stone. Another good example is food expiration detection. With material sensing, without opening the bottle, we can easily tell whether the milk is fresh or not. The last but not least, fake detection. For example, we know the Chanel perfume is very expensive. A lot of fake perfume are on the market. With material sensing, we can easily tell whether the perfume is fake or not. Traditionally, hyperspectral camera, X-ray, and radar are used for material sensing. However, these equipment are usually expensive and huge. So, in the last 2 years, several RF-based material sensing solutions have been proposed. For example, TagScan was published on MobileCom 17, and Liquid ID appears at MobileSense 18. So, the basic idea behind this two work is that when the RF signals penetrate through the target, the signal variation is very unique and can be used for material sensing. They move one big step in material sensing. However, there are still several limitations. The first limitation is that the sensing area is very limited. As we can see from the animation, the target needs to be placed exactly between the transmitter and the receiver, so that the direct path signal can penetrate through the target. Another issue is that they can only identify one target at the same time. The first target needs to be removed before the second target can be sensed. So think about a supermarket scenario where there are millions of items. Testing them one by one is not practical. So in this work, we ask ourselves one question: can we do a better job? Can we enable a larger sensing area? Can we sense multiple targets simultaneously? So following what we would like to achieve, we propose our system, Tagtag. We only need to attach a chip tag to the target to identify the material type and monitor the material change. Here, we want to emphasize is that the tag is very cheap, as low as 5 cents, and it's quite small and flexible to be attached to the target. We can see from the figure, our system can sense multiple targets simultaneously, and the targets are not restricted to be placed at a particular area. As long as the reader can communicate with the text, we are able to identify the material type. So let me explain the rationale behind Tagtag. The RFID tag is quite small but still have an antenna built in. Each tag antenna has an important property, impedance. One interesting observation is that when the tag is attached to the target, the tag antenna's impedance gets changed. So the theory behind this observation is that each antenna has an electromagnetic field. This field can be divided into two parts, far field and near field. When the target is in the far field, the impedance will not be changed. However, if the target is in the near field, the electrical current of the tag gets changed, and thus the impedance is changed. We further observe that the amount of impedance change is uniquely related to the material type. As we can see from the table, there are 3 different materials, and the corresponding impedance changes are quite different. So one big problem here is that the impedance cannot be easily measured. It can only be measured by the expensive vector network analyzer. However, a commodity RFID reader is not able to get the impedance information. So how can we use the commodity RFID reader to identify the material type? Fortunately, we observe that the impedance change can cause change of phase readings at the RFID reader. For RFID reader, we can easily get the phase readings. As we can see from the figure, for different types of materials, the impedance changes are very unique. This is also for phase changes. So in this work, we use the phase change as the material feature to identify the material type. However, there are still issues with employing the phase readings for material sensor. Let me explain what is the issue here. For phase change, the differential space is 0 to 2 pi. If there are a few materials, we can easily recognize these materials. However, with more and more materials added in, the spacing between adjacent materials becomes smaller and smaller. For example, the skim milk and sweet water are 2 different materials. However, the phase changes of these materials are quite similar. To solve this problem, we propose to hop to multiple channels to form a more unique material feature pattern. Let's look at, this is because the phase changes differently on different channels. Let's look at the example here. The phase changes for 2 different materials are very similar at the channel 915.5 MHz. However, when we hop to other channels, we can see that the phase changes are quite different. So with the built-in channel hopping function of RFID reader, we can combine the phase changes from multiple channels to form a more unique material pattern for sensor. So that's all about our design here. Next, I will introduce our challenges. Multiple challenges need to be addressed before our material pattern can work. I will go through all the challenges one by one. The first challenge is tag reader distance problem. As we can see from the figure, for different materials, the phase readings at the reader are quite different. However, even for the same material, when we change the tag reader distance, the phase readings at the reader are also different. So both the material type and tag reader distance can change the phase readings at the reader. For material sensor, we need to remove the impact of tag reader distance here. We propose a novel solution to move to the reader to a random nearby location. With these locations, we can get 2 pairs of phase and RSS readings, and we can write the equation like this. Since the 2 equations both contain the same term, d2 of d1, thus we can cancel off this term and remove the impact of tag reader distance. The second challenge is that the tag may be placed with a random orientation when attached to the target. So it's not practical for us to require the tag to be placed with, exactly with the same orientation. Random tag orientation does bring in phase change as the reader. To visualize this problem, let's look at the figure here. We wrote the tag, and we can clearly see that the phase readings vary with the tag rotation. To find a solution, we just discover something interesting here. When we rotate a tag to a random orientation, say 30 degrees, we can find that the phase readings change across multiple channels. However, the changes are the same across these channels. Thus, the overall shape of material pattern does not change. If we rotate the tag to another random degree, say 90 degrees, we can still see that the phase changes caused by the tag rotation are the same across multiple channels. Thus, we can conclude that the overall shape of material pattern does not change, just moved up and down. The next challenge is multipath effect. Multipath effect can distort the linear relationship between the phase and the frequency. If there is no multipath, the phase readings vary with the frequency linearly. To mitigate this multipath effect, we use a directional antenna, and then we pick clean channels. This is because we observe that with frequency hopping and a directional antenna, even in rich multipath environment like library, we are still able to identify more than 10 clean channels where we have a linear relationship. By picking the clean channels, where the multipath effect is greatly reduced. Okay, the last challenge, and maybe the most critical challenge, is liquid reflection interference. Different types of liquids can be divided into two groups: non-conductive and conductive liquids. The first group is non-conductive liquid. The typical example is oil. As we can see from the figure, for different amounts of oil, the impedance changes and the phase changes are quite the same. This is because there is no signal reflected from the oil. Next group is conductive liquid, and most liquids in our everyday life fall into this group. Take Pepsi as one example. As we can see, if for different amounts of Pepsi, the impedance changes are quite the same, but the phase changes are dramatically different. This is because the conductive liquid reflects signal to the tag and induce phase changes as the reader. What makes it challenging here? Different amounts of liquid Pepsi induce different amounts of phase changes as the reader. Let's look at the material pattern for Pepsi. If we add more Pepsi into the container, we can see that the material feature dramatically change. So with the liquid reflection interference, it's very challenging for us to obtain a stable material pattern for SenSys. We propose a novel solution to address this problem. Our solution is based on two observations. The first observation is that the phase values vary with the liquid thickness periodically. Most interesting here is that when the liquid thickness is integer times of half wavelength, there is no liquid reflection. So based on these two observations, we propose to derive reflection-free phase value. So if we can obtain the clean phase value without liquid reflection, we can obtain very clean and very stable material pattern for SenSys. We skip the details here and please refer to our paper for more details if you are interested. So for our implementation, we use an RFID reader, a directional antenna, and passive tags. We conduct experiments in 4 typical environments, like restaurant, retail store, library, and cafe, corresponding to different amounts of multipaths. We tested 23 different types of materials, including 16 liquids and 7 solids. The material identification accuracy is very high, almost 95%. Even though for the same material with slightly different concentrations, we can see that our results show that the identification accuracy is still very high. Now, I would like to show you some very interesting real-life applications. The first case study is anti-fake detection, where we would like to detect whether the perfume is fake or not. Here we have a total of 4 bottles of perfume, 2 are genuine and 2 are fake. From the figure, we can see that the material patterns for the genuine perfume are very similar. On the other hand, the material patterns for the fake perfume are quite different from that of genuine ones. These results demonstrate that our system is effective in detecting fake perfume. For the second case study, we would like to show our system can be applied to detect whether the milk is fresh or not. We expose 3 cups of fresh milk in the air at a temperature of 85 degrees. We can see that the material patterns for the 3 fresh milk are quite similar. However, after being exposed in the air for 30 minutes, we can see that the material patterns get dramatically changed. Our results show that after about 2 hours, our system can 100% detect the milk is not fresh anymore. So with all this, I would like to summarize our paper. First, we propose a novel system which uses the phase change caused by impedance change for material sensing. We address several challenges to make it work. We feel that the conductive liquid reflection is something really interesting. We also demonstrate our system with several very interesting applications like fake detection and food expiration detection. So that's all for my presentation today. Thank you for your time. I'm ready to take any question you will have.